Hello everyone, welcome to Theo-MathProblemSolver. In this particular episode, I'm so excited to take you through the journey of numerical integration. Specifically, we'll be looking at the Simpson's rule. What is the Simpson's rule about? So stay with me even as we do so. And at this point, if you have not subscribed, please do so. Like my content, turn on your notification button so that anytime I release new content, you'll be the first to receive that. And also, let's help spread this content to your colleagues, to your loved ones, and let's help demystify the myth around mathematics. Stay blessed. Let's get started. Now, numerical integration that we have started as we started in our previous episode, we kind of touched on and laid a foundation. We said that the reason for numerical integration is that sometimes there is there's some integrand. It almost seem impossible to find their antiderivative. Some integrand they seem almost impossible, so difficult to find the antiderivative. So sometimes we have to rely on another powerful, tool to be able to solve that. And that's why we have the numerical integration. Okay, and one powerful method under the numerical integration was called the Simpson's rule. Okay, so the same thing. Suppose we have this definite integral to approximate. Suppose we have this problem to approximate. Now, according to the Simpson's rule says that within the interval from A to B, let's have a lot of um, partitions. Let's sort of subdivide this interval, okay, into n equally sized subintervals with width. Okay, so we're going to have a width of B minus A on the n. The n, as I said, is n equally sized subintervals. Okay. And the n, I have to sort of mention that the n has to be even. Okay. So according to Simpson, n must be an even number. Okay. Must be an my s x and the n must be an even number. Okay. Now, according to Simpson, for us to find an approximate value of this, we kind of have to use this formula, and that the formula is b minus a all divided by 3n. Then we multiply by the expression within the square bracket. All right. So this is a formula that we are going to use to be able to solve a particular problem. And the easiest way, so what we are going to do is that I'm going to um, give an example, then we'll explain that. All right. So we are going to use this example to illustrate our understanding of the Simpson's rule. Okay. Very good. So let's see how best we can attack this particular in a problem. How do we do that? So from our previous example, we know that so all that we need to do is to so remember that we want to partition. Remember that we have this interval from 0 to 3, but we want to subdivide this into several partitions. Okay, but when you have 6 of that, and now remember that our width will be what? Will be B minus A on N, right? Before I touch on that, let me just explain this better so our weight, okay, per the formula, our weight is what? B minus A on N. But what is our A? Our B is the upper limit of this definite integral, and then our A is the lower limit. So in that case, that becomes 3 minus 0 over the n. The n is 6 per the given question. N is 6. So in which case, I will have 0.5. Okay. Now, what we're going to do, we're going to, we are going to um, um, we are going to divide this interval, which is from 0 to 3, okay, into several subdivisions, okay? So we're going to have several subdivisions. So it means that, so since our width is 0.5, it means we're going to have 0, then our next point will be 0.5, the next step will be 1, and then we're going to have this, okay? So we're going to have these partitions. Now, the next thing we need to do is that we are going to plug all of these values into the integrand. Remember that the integrand is f of x equal to e to the power x plus 1. Okay. Now, when we plug in 0, okay, so when we plug in this 0 into the integrand, we are going to have what? So it means wherever I see x in the integrand, I just replace it by 0. And that should give us what? 1.4142. And then we plug, the next we plug 0.5 into the function, and that should give us e to the power 0.5 plus 1, and that should give us 1.6275. Then we plug in 1, and that should give us e to the power 1 plus 1, and that should give us what? 1.92383. Then the next one, we also plug in 1.5. And 1.5, we're going to have e to the power 1.5 plus 1. And that should give us what? That should give us 2.3413. Okay. Then f of 2 should give us what? E to the power 2 plus 1. And that should give us what? That should give us 2.8964. Then and that should give us 3.6308. F of 3 should give us 4.55919. Is that okay? Then finally, what did we do? We plug that into our formula, and which means our x6 will be equal to 1 out of 6. And the 1 out of 6 is from the formula, okay? Remember that the form we have b minus a divided by 3n, okay? So all that we are doing is to kind of doing just an algebra, right? Yeah, you are just doing algebra here. So now per the formula, remember we have f of a, and f of a is f of 0. We have 4 multiplying f of x1. F of x1 is our 0.5, so that's all that we are doing. You're not doing anything different. So we're going to have, so remember our f of 0 was this particular value, which is 1.4142, then the 4 multiplying 1.6275 plus 2. So we have this, and then finally when we do our final roundup, we should have some value as this. So this is our final value. So it means that the area under the curve within the domain 0 to 3, we're going to have this as our area, okay, which is also close to the to the to the approximate or to the value that we're given initially, and the value that we're given initially was also close to such value. And at this point, if you have not, subscribed, please do so. Like my content and help spread this content to your colleagues, to your loved ones, and let's create a community where there will not be math phobias, but rather people who are willing to take on the cost, who are willing to sort of use mathematics to solve real world problems. So thank you so much for your time, and I'm so excited to have you on my platform and my community as well. Thank you so much.